There's a place on Earth under the quiet farmland where cows graze across valleys. There is a wound deep beneath, a circle carved through limestone and clay, so vast that it passes under two nations without either noticing. This is not a mine. This is not a bunker. This is a telescope pointed not at the stars but inward at the very fabric of what we call real. For decades, humans have known the universe is broken. Not broken in the way a machine breaks, but broken in the way a mirror cracks, in the way a promise fails. The equations that describe everything, that predict how particles move and forces interact, they work beautifully. They work so well that physicists have built entire careers on their precision. But there are holes, tiny fractures in the mathematics that no one can explain. And the machine beneath the Alps was built to find those fractures, to press on them until they split open and reveal what is hiding underneath. What they have found in recent years has shaken the foundations of physics in ways that most people will never understand. This is the story of what happens when you look too closely at reality and what happens when reality looks back. The tunnel stretches 17 miles in a perfect circle, buried 100 meters beneath the surface. Above it, people live their ordinary lives. They plant crops, they repair roofs, they argue about politics and worry about money. They have no idea that directly beneath their Sunday picnics, protons are screaming through a vacuum at speeds that would take them around the entire planet 7 times in a single heartbeat. The machine itself is a cathedral of cold. Thousands of superconducting magnets line the tunnel, each one wrapped in cables thinner than a spider's silk but stronger than any steel ever forged. To function, these magnets must be cooled to minus 456 degrees Fahrenheit. That is colder than the space between galaxies, colder than the darkest void where no star has ever burned. The machine requires 96 tons of liquid helium just to maintain that impossible cold. And if the temperature rises by even a fraction of a degree, the entire system fails in a cascade of catastrophic warmth. Inside this frozen ring, 2 beams of protons travel in opposite directions. Each beam contains billions of particles, each one stripped down to its bare nucleus, each one carrying a positive charge that makes it respond to magnetic fields. They race around the circle 11,000 times every second, gaining energy with every lap until they are moving at 99.999% of the speed of light. At those speeds, strange things happen. Time itself begins to warp. The protons experience the passage of seconds differently than we do. They age slower. They exist in a kind of temporal suspension, frozen in their frantic orbit, while the world above them turns through days and years and decades. And then, at 4 points around the ring, the beams are made to cross. The collision is not gentle. It is not slow. Billions of protons slam into billions of other protons at combined energies of 13 trillion electron volts. The impact point is smaller than a single atom. The temperature at that point reaches several trillion degrees, hotter than the center of any star, hotter than anything that has existed in the universe since the first heartbeat of creation. In that microscopic inferno, energy transforms into matter. Particles that have not existed since the universe was younger than a trillionth of a second suddenly flash into being, exist for less than an instant, and then decay into showers of debris that detectors the size of cathedrals capture with exquisite precision. This is what CERN does. It rewinds creation. It takes us back to conditions that existed when the universe was so young that time itself had barely begun to tick. And in that chaos, physicists are looking for something specific. They are looking for the crack. For 50 years, physicists had a problem they could not solve. Their equations described the behavior of particles beautifully. They predicted how forces operated, how matter interacted, how the universe held itself together. But there was a hole in the mathematics, a gap that made no sense. The equation said particles should have no mass. Zero. Nothing. Every electron, every quark, every fundamental piece of matter should weigh exactly nothing and fly through the universe at the speed of light. Obviously, this is wrong. You have mass, the chair beneath you has mass, the planet has mass. Something in the equations was missing, and in 1964, several physicists proposed an answer. There must be a field, an invisible field that fills all of space. When particles move through this field, they interact with it. That interaction creates drag, and that drag is what we experience as mass. Think of it like walking through water. In air, you move freely. In water, resistance slows you down. The Higgs field works the same way, except the resistance does not slow particles, it gives them weight. If this field exists, the mathematics said it should produce a particle, a quantum of the field itself. They called it the Higgs boson. But finding it would be nearly impossible. The Higgs boson is unstable. It exists for less than a trillionth of a second before decaying into other particles. You cannot catch it. You cannot hold it. You can only see the debris it leaves behind and work backward. For decades, physicists searched. They built larger and larger colliders. They analyzed billions of collisions. They found nothing. Some began to wonder if the particle was real at all. Maybe the theory was wrong. Maybe mass came from something else entirely. Then came July 4th, 2012. In a packed auditorium at CERN, scientists announced they had found it. The Higgs boson was real. The data was overwhelming. Two separate detectors using two completely different methods had both captured its signature. The statistical certainty was 5 sigma, meaning the chance of error was less than 1 in 3 million. The room erupted. Peter Higgs, the physicist who had proposed the field 48 years earlier, sat in the audience with tears running down his face. He had waited half a century to know if his mathematics described reality. It did. But the discovery created new mysteries. The Higgs boson has a specific mass about 125 billion electron volts, and that number is strange. It sits in a narrow range that suggests the universe might be unstable. The vacuum itself might be capable of collapsing into a lower energy state, destroying everything. This is theoretical, unconfirmed, but the mathematics allow it. And there is something else, something the equations predicted that has still never been observed directly. The Higgs boson should be able to interact with itself. What that means for the fate of everything is still being calculated. Every particle in the standard model interacts with other particles. Electrons repel electrons. Quarks bind to quarks. Photons bounce between charged objects. These interactions follow rules, predictable patterns that physicists have tested millions of times. But the Higgs boson is different. According to theory, the Higgs can do something no other fundamental particle can do. It can interact with copies of itself. 3 Higgs bosons meeting at a single point. 4 Higgs bosons connecting in a single event. This self-interaction is written into the mathematics. It must happen. The problem is proving it. Finding 1 Higgs boson required decades of work and billions of collisions. Finding 2 Higgs bosons at the same time is roughly 1,000 times harder. The probability is so low that even with the massive amounts of data CERN collects, the events are rare. But scientists are searching. The reason this matters goes far beyond particle physics. The Higgs self-coupling, as it is called, determines the shape of the Higgs potential. Think of this potential as a landscape. The field sits in a valley. The shape of that valley controls how the universe behaves. If the valley is deep and stable, the universe will remain as it is forever. But if the valley has a thin wall and a deeper pit exists on the other side, the universe could tunnel through. Quantum mechanics allows this. A random fluctuation could push the field over the edge. What happens next is called vacuum decay. A bubble of true vacuum would form. Inside the bubble, physics would operate differently. The constants that govern atoms, forces, and light would all change. The bubble would expand at the speed of light, consuming everything it touched. You would never see it coming. One moment, reality exists. The next moment, it does not. This is theoretical. There is no confirmed evidence that vacuum decay will happen. The mathematics suggest it is possible, but the timescale might be longer than the age of the universe. We might be safe for trillions of years, or we might not be safe at all. The only way to know is to measure the Higgs self-coupling precisely. Right now, CERN has constrained the value. They know it lies within a certain range, but the uncertainty is still large. The data shows the coupling exists somewhere between 0.7 and positive 6 times the predicted standard model value. That is a wide window. The next generation of experiments will narrow it. If the coupling matches the standard model exactly, the universe is probably metastable, balanced on a knife edge between existence and annihilation, but likely to remain balanced for an unimaginably long time. If the coupling deviates, something is wrong with our understanding of physics itself. Either answer changes everything. And while physicists chased the Higgs into its own reflection, something else was happening in the frozen depths of the machine, something that required cold beyond imagination. Between galaxies where no stars burn and no planets spin, the temperature drops to about minus 454 degrees Fahrenheit. This is the natural cold of the void. The background radiation left over from the birth of the universe keeps space from reaching absolute zero, but just barely. The Large Hadron Collider operates colder than that. The superconducting magnets that bend the particle beams require temperatures of minus 456 degrees Fahrenheit, almost 2 degrees colder than intergalactic space, almost as cold as physics allows anything to be. Reaching this temperature requires a system of staggering complexity. 96 tons of liquid helium circulate through the machine. Helium is the only substance that remains liquid at these extremes. Everything else freezes solid. The helium must be continuously pumped, monitored, and recycled. Even a tiny leak would cause catastrophic warming. In 2008, exactly that happened. During the initial startup, a faulty electrical connection caused a spark. The spark heated a small section of the machine. That heat caused helium to vaporize explosively. The pressure wave damaged over 50 magnets and ripped vacuum pipes from their mountings. The repairs took 14 months. The cost reached millions of dollars. The machine is fragile despite its size. A bird dropping a piece of bread on an outdoor power unit once caused a shutdown. A weasel chewing through electrical cables knocked the system offline. Engineers have learned to expect the unexpected. But when the cold holds, something remarkable happens. The superconducting magnets lose all electrical resistance. Current flows through them without any loss of energy. In a normal wire, electricity generates heat. That heat wastes power and limits how much current you can push through. Superconductors have no such limit. The same current can circulate forever without adding any energy. This is what allows the magnets to generate fields powerful enough to bend particles moving at near light speed. A conventional magnet would melt. A superconducting magnet simply bends space around itself. There are 1,232 dipole magnets in the main ring. Each one is nearly 50 feet long and weighs 35 tons. Together, they contain enough niobium-titanium wire to wrap around the equator twice. The precision required to align them is measured in fractions of a millimeter. If any magnet fails, the beam loses control. Particles moving at close to light speed would slam into the tunnel walls. The energy they carry is equivalent to a speeding train. The machine has emergency systems that can dump the beam into a graphite absorber within 3 laps of the ring, less than 1,000th of a second. But the margin for error is razor thin. Everything must work perfectly. The cold must hold. The magnets must fire. The beams must stay aligned. When they do, the collider becomes a time machine. And in 2023, it was pointed at the strangest target yet. Something that should not exist. Something that seems identical to matter, yet vanished almost completely from the universe. The experiments at CERN were about to drop antimatter. Every particle has a twin, an opposite, an antimatter counterpart that carries reverse charges, but otherwise looks identical. The electron has the positron. The proton has the antiproton. When matter and antimatter meet, they annihilate each other completely, converting all their mass into pure energy. This is confirmed physics measured countless times. Undeniable. But one question remained unanswered for decades. Does antimatter fall up or down? It sounds strange. Why would antimatter behave differently in a gravitational field? General relativity. Einstein's theory of gravity predicts that everything falls the same way regardless of its composition. A feather and a hammer dropped in a vacuum hit the ground at the same moment. Antimatter should follow the same rule. But no one had ever tested it directly. The problem is keeping antimatter alive long enough to drop. As soon as an antiparticle touches ordinary matter, both are destroyed. You cannot hold antimatter in your hand. You cannot place it on a scale. You cannot simply let go and watch what happens. CERN built a machine to solve this problem. The alpha experiment creates antihydrogen atoms by combining antiprotons with positrons. These antiatoms are electrically neutral, which means they can be trapped using magnetic fields rather than electric ones. The trap suspends the antihydrogen in a vacuum, preventing any contact with normal matter. In 2023, the team was ready. They created a cloud of anti-hydrogen atoms inside a vertical cylinder surrounded by superconducting coils. Then slowly they weakened the magnetic trap. The anti-atoms began to escape. Some drifted upward, some drifted downward. When each one touched the cylinder wall, it annihilated and released a flash of energy. Detectors recorded where each flash occurred. 80% of the antimatter annihilated below the center of the trap, only 20% annihilated above. The conclusion was clear. Antimatter falls down. It responds to gravity the same way ordinary matter does. Einstein was right. This might seem like the end of the story. The experiment confirmed what theory predicted, but the implications run deeper. If matter and antimatter behave identically under gravity, why is the universe made almost entirely of matter? The Big Bang should have produced equal amounts of both. They should have annihilated each other completely, leaving nothing behind but radiation. Something broke the symmetry. Something caused matter to win by a tiny fraction, 1 part in a billion. That small imbalance is why galaxies exist, why stars burn, why you are here to wonder about it. The Alpha experiment ruled out one explanation. Antimatter does not fall up. Gravity is not the reason for the imbalance. So what is? CERN is now producing antimatter at unprecedented rates, over 2 million anti-atoms in the 2023 and 2024 runs alone. The precision of the measurements keeps increasing. But while some scientists chased falling antimatter, others were chasing something even stranger, a wobble in the spin of a particle that refused to match the mathematics. For years, that wobble threatened to break physics entirely. The muon is the electron's heavier cousin, 200 times more massive, but otherwise similar. It carries the same negative charge. It responds to the same forces. It should obey the same rules. But when physicists measured how muons spin in a magnetic field, something was wrong. Every charged particle with spin acts like a tiny magnet. Place it in an external magnetic field, and it wobbles like a spinning top that slowly tilts. The rate of that wobble can be calculated using quantum mechanics. The standard model predicts it with extraordinary precision out to 10 decimal places. The measurement should match the prediction. In the late 1990s, an experiment at Brookhaven National Laboratory found a discrepancy. The muon wobbled slightly faster than the mathematics said it should. The difference was small, incredibly small, but it was there. Physicists call this quantity G-2. The G represents the gyromagnetic ratio, a number that should equal exactly 2, according to basic quantum theory. Quantum corrections push it slightly higher, which is why the measurement is called G-2. The Brookhaven result suggested the corrections were larger than expected. If true, something was interacting with the muon that the standard model did not include a new particle, a new force, something hidden in the quantum foam that surrounds every particle. But the problem was statistics. The Brookhaven measurement was precise, but not precise enough to claim discovery. It hovered around 3 to 4 sigma, meaning there was still a small chance the discrepancy was random noise. CERN contributed data. Fermilab built a new experiment. The magnet from Brookhaven was transported across the country on a barge because it was too large to move any other way. Scientists spent years preparing. In 2021, Fermilab released its first results. The discrepancy held. The muon still wobbled wrong, but the theoretical prediction was also changing. Calculating the muon's wobble requires adding up contributions from every particle it could interact with. Quarks, gluons, photons, and more exotic possibilities all contribute. Some of these calculations require supercomputers running for months. Others require experimental data from colliders to constrain the inputs. Different methods gave different answers. One approach, using data from electron-positron collisions, supported the anomaly. Another approach, using a technique called lattice quantum chromodynamics, suggested the standard model might be correct. After all, the two methods disagreed with each other. In June 2025, Fermilab released its final results using all 6 years of collected data. The experimental precision had reached unprecedented levels. The measurement agreed closely with the revised theoretical prediction. The anomaly that had haunted physics for 25 years had faded, but it did not disappear entirely. Tensions remain between different calculation methods. The mystery has shifted from the experiment to the theory. Some physicists believe new physics is still hiding in the numbers. Others believe the Standard Model has survived another test. But while the muon wobble cooled down, another crisis was heating up. A different particle had weighed in heavier than expected, and that measurement nearly shattered everything. The W boson is a carrier of the weak nuclear force. It mediates certain types of radioactive decay. It is essential to how particles transform into other particles, and its mass is one of the most precisely predicted values in all of physics. The Standard Model says the W boson should weigh approximately 80,357 million electron volts. This prediction comes from measuring other particles and plugging their values into interconnected equations. Everything must balance. If one number is off, the whole structure wobbles. In 2022, the CDF experiment at Fermilab dropped a bomb. After analyzing data collected over decades, they announced a new measurement of the W boson mass. Their value was 80,433 million electron volts. That is 76 million electron volts higher than the prediction. The discrepancy was 7 sigma. That means the chance of it being a statistical fluke is less than 1 in a trillion. If correct, the Standard Model was broken. Physicists scrambled to understand what it could mean. Some proposed new particles that had escaped detection. Others suggested the Higgs boson might interact with undiscovered forces. A few speculated about extra dimensions or supersymmetric partners, but there was a problem. Other experiments did not agree. Measurements from CERN, from earlier experiments at Fermilab, from the Large Electron-Positron Collider, all gave values closer to the Standard Model prediction. The CDF results stood alone. Either CDF had discovered something revolutionary or they had made an error. Measuring the W boson mass is extraordinarily difficult. The particle decays into a muon-onda neutrino. Muons can be tracked precisely, but neutrinos escape the detector without interacting. You cannot measure the neutrino directly. You must infer its properties from what is missing in the collision. This requires perfect understanding of the detector. Every magnetic field, every material interaction, every calibration must be known exactly. Small systematic errors can shift the final result. For 2 years, the physics community waited. Then, in September 2024, the CMS experiment at CERN released its own measurement. Using 300 million collision events and the most advanced techniques ever applied, they found the W boson mass to be 80,360 million electron volts, almost exactly what the Standard Model predicted. The CDF anomaly did not replicate. The crisis appeared to be over, but mysteries remain. Why did CDF get such a different answer? Their analysis methods have not been shown to contain obvious errors. Some physicists believe undiscovered systematic effects may explain the difference. Others wonder if the disagreement hints at something deeper. For now, the Standard Model has survived. The W boson weighs what it should, but just because one crack sealed does not mean others have not opened. In the debris of collisions, scientists found particles that should not exist at all. Quarks are the building blocks inside protons and neutrons. They come in 6 types called flavors: up, down, charm, strange, top, and bottom. Normally, quarks combine in simple patterns. 3 quarks make a baryon like the protons in your body. 2 quarks, specifically 1 quark and 1 antiquark, make a meson. For decades, these were the only combinations observed, but the theory allowed more. 4 quarks bound together, 5 quarks locked in a single particle. These exotic states were predicted in the 1960s at the same time the quark model was invented. Yet no one could find them. Then the Large Hadron Collider started smashing particles. The LHCb detector specializes in studying bottom quarks and charm quarks. These heavy quarks live just long enough to travel a fraction of a millimeter before decaying, leaving distinctive tracks that can be reconstructed with precision. By analyzing those tracks, physicists began finding things that did not match any known particle. In 2015, LHCb announced the first confirmed pentaquark, 5 quarks bound together. The particle contained a charm quark, a charm antiquark, and 3 light quarks. It existed for only an instant before falling apart, but the signal was unmistakable. Then came the tetraquarks. In 2020, the collaboration found a particle made of 4 charm quarks, 2 charms, and 2 anticharms bound in a tight cluster. This was extraordinary. All previous tetraquarks had contained a mix of heavy and light quarks. This one was purely heavy. The discovery changed how physicists think about the strong force. In 2022, the announcements accelerated. 3 new exotic particles in a single report. A pentaquark containing a strange quark, the first of its kind. A pair of tetraquarks, one with double electric charge and one neutral, appearing together in the K. The statistical significance was overwhelming. 15 sigma for the pentaquark, 6 sigma for the tetraquarks. These were not random noise. These were real objects. But what exactly are they? 2 models compete. In one, the quarks bind tightly together into a single compact object. In the other, the particle is more like a molecule. 2 ordinary hadrons held loosely near each other by residual strong force, not fully merged, but not quite separate. The answer matters. Understanding how quarks bind helps explain the strong force itself, one of the 4 fundamental forces of nature. It also helps physicists calculate what should happen in extreme environments like the cause of neutron stars or the first moments after the Big Bang. More than 60 new hadrons have been discovered at the LHC. Most are exotic states that had never been observed before. The particle zoo is growing. And among those new arrivals, scientists found something that connected quantum mechanics to energies never before tested. 2 particles entangled across space-time, behaving as one. Quantum entanglement is one of the strangest phenomena in physics. When 2 particles become entangled, their properties are linked. Measure one and you instantly know something about the other, no matter how far apart they are. Einstein called it spooky action at a distance. He did not believe it could be real, but it is real. Experiments have confirmed entanglement countless times using photons, electrons, and atoms. The particles behave as a single system, even when separated by miles. The 2022 Nobel Prize in Physics was awarded specifically for experiments proving that entanglement is genuine and that hidden variables cannot explain it. However, all previous experiments occurred at low energies, tabletop setups, lasers and crystals, and cold atoms. The quantum effects were gentle, contained, safe. No one had observed entanglement at the violent energies inside a particle collider until 2023. The Atlas collaboration at CERN announced they had detected quantum entanglement between top quarks. These are the heaviest fundamental particles known to exist. Each one weighs about as much as an entire gold atom. They are created only in the most extreme collisions. Top quarks are also unstable. They decay in less than a trillionth of a second. There is no time for them to interact with other particles or exchange information. Their quantum properties must be measured through the debris they leave behind. The experiment focused on pairs of top quarks produced when protons collided. By measuring the angles between the decay products, physicists could infer the spin states of the original quarks. If the spins were correlated in a specific way, it would prove entanglement. The result exceeded 5 sigma. Entanglement was confirmed. The energy scale was staggering, over 1 trillion times higher than previous entanglement experiments. The particles were created in conditions that existed only 1 trillionth of a second after the Big Bang. The CMS collaboration replicated the finding with their own data. They went even further, examining pairs of quarks moving at high relative speeds where classical communication between the particles would be impossible, even at the speed of light. Entanglement still held. This matters for more than just confirming quantum mechanics. The techniques used to detect entanglement at the LHC could be applied to search for new physics. Any deviation from the predicted spin correlations would indicate unknown particles or forces interfering with the system. So far, no deviations have been found. The standard model continues to describe reality at the highest energies we can test. Quantum mechanics remains unbroken. Entanglement works exactly as the mathematics says it should, even in the most violent environment humans can create. But confirming the old theories was never the main goal. CERN exists to find what lies beyond. And in the subtle differences between matter and antimatter, scientists found a clue that might explain why the universe exists at all. The Big Bang should have produced equal amounts of matter and antimatter. Every equation, every symmetry principle, every fundamental law points to perfect balance. When energy converts to mass, it creates pairs. One particle, one antiparticle, always equal. Yet look around you. Everything is matter. The air you breathe, the stars overhead, the most distant galaxies. Matter won, antimatter lost. The asymmetry is tiny. For every billion antimatter particles created in the Big Bang, there were 1 billion and 1 matter particles. That tiny excess is all that survived the mutual annihilation. Everything you see in the universe comes from that one particle in a billion. Something broke the symmetry. Physicists call it CP violation. The C stands for charge conjugation, swapping particles for antiparticles. The P stands for parity, looking at the mirror image of a process. If physics is perfectly symmetric, then flipping both charge and parity should give identical results. But it does not. In 1964, experiments showed that certain particles decay slightly differently than their antiparticles. The effect was small but real. CP violation exists in the Standard Model encoded in the mathematics of quark mixing. The question is whether the known CP violation is enough to explain the matter-antimatter asymmetry. Most physicists say no. The Standard Model effect is too weak by many orders of magnitude. Something else must be happening. CERN has been searching. The LHCb experiment specializes in studying CP violation. It examines decays of particles containing bottom quarks and charm quarks, looking for tiny differences between matter and antimatter versions. In 2025, the collaboration announced a breakthrough. They had observed CP violation in baryons for the first time. Baryons are particles like protons and neutrons made of 3 quarks. Previously, CP violation had only been confirmed in mesons, which contain 2 quarks. The measurement involved 2 types of particles containing bottom quarks. By comparing how often they decayed through different pathways, physicists detected the asymmetry. This does not solve the mystery. The observed CP violation is still too small to explain why matter dominates the universe, but it confirms that baryons behave differently from their antimatter counterparts. More channels remain to be explored. Each new measurement constrains the possibilities. Each new confirmation of Standard Model predictions pushes the unknown further into the corners. If the Standard Model cannot explain the asymmetry, new physics must exist, and new physics would mean new particles, new forces, new interactions that have hidden from every experiment so far. The universe is made of matter because something we do not understand made it that way. Finding that something is why CERN keeps smashing particles together. But the matter we can see is only a fraction of what exists. Most of the universe is invisible. Everything the Large Hadron Collider studies, every proton, every quark, every Higgs boson, all of it adds up to about 5% of the universe. 5%. The rest is dark. Not dark as in distant or faint. Dark as in undetectable by any instrument ever built. Matter that does not emit light, does not absorb light, does not interact with normal matter except through gravity. We know it exists because of how galaxies move. In the 1970s, astronomer Vera Rubin measured the rotation speeds of stars in distant galaxies. The stars at the edges should have been moving slower than the stars near the center, the same way outer planets orbit more slowly than inner ones. That is how gravity works with visible mass. But the outer stars were moving too fast. Much too fast. The only explanation was invisible mass pulling on the stars with gravity, but remaining otherwise undetectable. Dark matter is confirmed by multiple independent observations. Gravitational lensing, where light bends around invisible mass. The cosmic microwave background, where tiny temperature variations reveal the structure of the early universe. The formation of galaxies, which could not have occurred without dark matter seeds. The evidence is overwhelming. Something is there, but no one knows what. Particle physicists have proposed many candidates. Weakly interacting massive particles, or WIMPs, were the leading theory for decades. Heavy particles that interact only through gravity and the weak force left over from the Big Bang, like cosmic relics. CERN has searched for WIMPs. If they exist and have the right properties, they should occasionally be produced in high-energy collisions. They would escape the detectors without interacting, creating events with missing energy. No such events have been found. The search continues. Other candidates remain possible. Axions, hypothetical light particles, propose to solve a different problem entirely. Sterile neutrinos, cousins of ordinary neutrinos that do not feel the weak force. Primordial black holes formed before the first stars. Dark energy is even stranger. In 1998, astronomers discovered that the expansion of the universe is accelerating. Something is pushing space apart faster and faster. That something has been named dark energy. but the name hides our ignorance. No one knows what it is. Dark energy makes up about 68% of the universe. Dark matter accounts for another 27%. Ordinary matter, the atoms and particles and everything we can touch, fills the remaining 5%. CERN cannot study dark energy directly. The energies involved are far below what colliders can probe. But if dark matter is made of particles, there is a chance the LHC can produce them. Every collision is a lottery ticket. Every spray of debris is search for signs of something escaping, something invisible, something new. So far, the searches have come up empty. But absence of evidence is not evidence of absence. The particles might be lighter than expected, heavier than expected, interact through forces we have not imagined. The hunt continues, and while physicists searched for what they could not see, they also recreated something that has not existed for nearly 14 billion years. For 1 month, each year the Large Hadron Collider changes its diet. Instead of protons, it accelerates lead nuclei. Heavy ions containing 82 protons and 126 neutrons, each stripped of all their electrons and pushed to nearly the speed of light. When these lead nuclei collide, the result is unlike anything else the machine produces. The energy density is so extreme that protons and neutrons melt. The quarks and gluons that normally stay locked inside hadrons break free. They form a new state of matter, something that has not existed naturally since the first microsecond after the Big Bang. Physicists call it quark-gluon plasma. Imagine a soup, not a soup of molecules or atoms, but a soup of the fundamental constituents of matter. Quarks swimming freely, interacting with gluons, behaving as a collective liquid rather than individual particles. This plasma is the hottest substance humans have ever created. Temperatures exceed several trillion degrees, hotter than the core of any star by a factor of 100,000. So hot that the strong force which normally binds quarks into protons and neutrons temporarily loses its grip. The Alice detector was built specifically to study this plasma. Its name stands for a Large Ion Collider experiment. While other detectors search for rare events and near-event new particles, Alice analyzes the bulk properties of thousands of particles produced simultaneously. What they found surprised everyone. The quark-gluon plasma behaves like a nearly perfect liquid. It flows with almost zero viscosity, meaning internal friction is as low as physics allows. This was unexpected. Theorists had predicted a gas-like state, particles bouncing chaotically with no collective behavior. Instead, the plasma moves like water. Ripples and waves propagate through it. Patterns emerge that reveal the initial geometry of the collision. Understanding this plasma helps explain the early universe. In the first microsecond after the Big Bang, the entire cosmos was filled with quark-gluon plasma. As space expanded and temperatures dropped, the plasma cooled. Quarks and gluons condensed into protons and neutrons. Those protons and neutrons eventually formed hydrogen and helium, the raw material for the first stars. Every atom in your body passed through this phase. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it was once quark-gluon plasma. The LHC allows scientists to study those first moments directly. The experiments have also revealed unexpected connections. The plasma produces more strange quarks than simple models predicted. Particles containing strange quarks appear at enhanced rates, suggesting the plasma environment favors their creation. There are also hints of collective behavior in smaller collisions. Even proton-proton events sometimes show flow patterns similar to heavy ion collisions, as if many droplets of plasma form and evaporate almost instantly. The boundary between normal matter and exotic matter is blurrier than anyone expected. Each year brings new data. Each year pushes understanding deeper into the first moments of creation. But even deeper mysteries waited, rare events that took thousands of years of accumulated collisions to observe. Some events at the Large Hadron Collider are common. Protons scatter, quarks spray outward, jets of particles flood the detectors billions of times per day. Other events are rare. So rare that even with 600 million collisions per second, they might appear only a handful of times per year. Physicists must wait. They must accumulate data. They must sift through trillions of events to find the needle in the haystack. The Higgs boson decaying into a pair of muons is one of those needles. The Higgs can decay many ways: into bottom quarks about 58% of the time, into W bosons about 21%, into pairs of top particles about 6%. These decay modes have all been observed and measured, but the decay into muons is far rarer. Only about 0.02% of Higgs bosons take this path. The signal is buried under backgrounds. Other processes produce muon pairs far more often than the Higgs does. Extracting the signal required ingenuity. Physicists developed new analysis techniques. Machine learning algorithms trained on simulated data learned to recognize the subtle signatures of Higgs decays. Advanced statistical methods squeezed every drop of information from the measurements. In 2020, Atlas announced the first evidence. The signal exceeded 3 sigma, strong but not definitive. CMS found similar results. The hints were there, but confirmation required more data. By 2024, the combined results reached the threshold for discovery. The measurement matters because it reveals how the Higgs boson interacts with second-generation fermions. The muon is the heaviest particle in the second generation. Its coupling to the Higgs should follow a precise pattern based on its mass. If the coupling were different than expected, it would indicate new physics. Perhaps the Higgs is not alone. Perhaps other particles contribute to mass in ways the standard model does not describe. So far, the measurement matches the prediction, but precision continues to improve. Every new dataset narrows the uncertainty. Every analysis refinement sharpens the picture. A similar story played out with another rare decay, the Higgs transforming into a Z boson and a photon. This process is even more suppressed, occurring in less than 0.1% of decays. Evidence for this channel appeared in 2022. Full observation remains a goal for the next runs. These rare decays test the standard model at its most delicate points. They probe quantum loops where virtual particles flicker in and out of existence. Any discrepancy could reveal particles too heavy to produce directly, but light enough to influence the mathematics. Thousands of years of equivalent collision time have accumulated in the detectors. The samples grow larger, the measurements grow sharper, and with each improvement, the noose tightens around whatever new physics might be hiding. But new physics has hidden well, which raises a troubling question. If the standard model keeps working, what does that say about the universe we live in? The Higgs boson has a mass of about 125 billion electron volts. That number is not random. It was not guaranteed. In principle, the mass could have been almost anything, higher, lower, different by a factor of 2 or 10 or 1,000. But the specific value we measured has disturbing implications. The mass of the Higgs combined with the mass of the top quark determines whether the vacuum is stable. In quantum field theory, the vacuum is not empty. It is the lowest energy state of all the fields that fill space. The Higgs field sits in its potential like a ball resting at the bottom of a valley. Small disturbances roll the ball slightly, but it always returns to the lowest point unless the valley has a hidden cliff. If the Higgs potential changes shape at very high field values, a deeper minimum could exist. The current vacuum would be a false vacuum, a local minimum rather than the true bottom. Quantum mechanics would allow the field to tunnel through the barrier like a ball spontaneously appearing on the other side of a wall. If that happens, a bubble of true vacuum forms. Inside the bubble, physics changes. The Higgs field takes a new value. Particle masses shift. The forces between atoms alter. The bubble expands at the speed of light, destroying everything it touches. Is our vacuum stable or metastable? The answer depends on precise measurements. The current data places us very close to the boundary. The central values suggest metastability, a vacuum that could decay, but with a lifetime much longer than the age of the universe. This is not cause for immediate concern. Even if the vacuum is metastable, the probability of decay in our observable universe within the next several billion years is negligible. But it raises deep questions. Why does the universe sit so close to the edge? Is it coincidence? Is it a sign of new physics that stabilizes the vacuum at higher energies? Does the multiverse select for vacuums that last long enough to produce observers? The Higgs self-coupling measurements will help answer these questions. If the coupling matches as the standard model exactly, the metastability conclusion strengthens. If it deviates, new particles or interactions might exist that change the high-energy behavior of the potential. Either way, we learn something profound. The universe we live in might be balanced on a knife edge between eternal existence and sudden annihilation. The Higgs field that gives particles mass might also be capable of erasing everything. This sounds alarming. It is not meant to be comforting, but it is also true that physics has always revealed uncomfortable facts about our situation. The Earth is not the center of the universe. The stars are not eternal. The cosmos will eventually go cold and dark. Adding another layer of existential uncertainty changes nothing about daily life, but it changes everything about how we understand reality. And reality keeps revealing new layers. Imagine a sombrero, a hat with a raised center and a brim that curves down all around. Turn that hat upside down. Now you have a shape that resembles the Higgs potential. In the center, a peak. Around the peak, a circular valley at lower energy. Anywhere along that valley floor is equally stable. The Higgs field can point in any direction around the circle and find the same minimum energy. This is called spontaneous symmetry breaking. The original equations are perfectly symmetric. Nothing prefers one direction over another, but the field must choose. It must settle somewhere in the valley. The moment it chooses, the symmetry breaks. The direction it points becomes special. That choice gave particles their masses. Before the symmetry broke, in the first trillionth of a second after the Big Bang, the universe was symmetric. The electromagnetic force and the weak nuclear force were unified into a single electroweak force. All particles were massless. Everything moved at the speed of light. Then the temperature dropped. As the universe cooled, the Higgs field rolled into its valley. Symmetry broke. The electroweak force split into electromagnetism and the weak force. Particles that interacted with the Higgs gained mass. Those that did not, like the photon, remained massless. The shape of the Mexican hat potential controls all of this. If the peak in the center were higher or lower, the amount of symmetry breaking would change. Particle masses would shift, the chemistry that allows life would fail. Stars might not burn, atoms might not form. Measuring the Higgs self-coupling tells us the exact curvature of the hat. How steep is the central peak? How deep is the valley? How does the shape extend beyond the valley floor? At field values, we cannot probe directly. These questions connect particle physics to cosmology. The shape of the potential affected inflation, the rapid expansion of the early universe. It affects the nature of the electroweak phase transition the moment when symmetry broke. It affects what happens if the universe reaches extreme conditions again. Perhaps during the collapse of the collision of black holes, everything traces back to the hat. CERN cannot see the full shape directly. The energies required are far beyond any machine. But by studying the Higgs boson and its interactions, physicists can infer the local curvature. They can constrain models. They can rule out possibilities. The current data suggests the hat is shallow enough that the vacuum might be metastable. The peak is just high enough to keep us in the valley, but not so high that we are safe forever. New physics could change the shape. Supersymmetric partners, if they exist, would add contributions that stabilize the potential. Extra Higgs particles would alter the curvature. Interactions with dark matter could reshape the entire landscape. Finding any of these would reveal what the hat truly looks like. And if the hat has hidden features, they might explain mysteries we have not yet imagined. The search for those features requires bigger machines. The Large Hadron Collider has been operating since 2008. It discovered the Higgs boson. It confirmed quantum entanglement at extreme energies. It found dozens of exotic particles and tested the standard model to unprecedented precision. But it has limits. The tunnel is 17 miles around. The magnets cannot be made much stronger with current technology. The energy cannot increase significantly without building something new. CERN is planning something new. The future circular collider would be 4 times larger, a tunnel nearly 62 miles in circumference, burrowing beneath the Jura Mountains and Lake Geneva. It would start as an electron-positron collider producing Higgs bosons with extraordinary precision. Later, it would upgrade to a hadron collider with collision energies of 100 trillion electron volts, 7 times more powerful than today's machine. The precision gains from the electron-positron phase would be immediate. Electrons and positrons are fundamental particles. When they collide, all their energy goes into creating new particles. There are no leftover quarks, no spray of debris, no messy backgrounds. This cleanliness allows measurements that hadron colliders cannot match. The Higgs boson couplings could be measured to within 1% or better. Any deviation from the standard model would stand out clearly. If the Higgs is hiding secrets, the future circular collider would expose them. The later hadron phase would explore uncharted territory. At 100 trillion electron volts, particles too heavy for the LHC could be produced directly. Supersymmetric partners, if they exist at the relevant mass scale, would appear. New gauge bosons, predicted by theories that extend the standard model, could be discovered. The machine would also improve searches for dark matter candidates. If weakly interacting particles exist with masses in the right range, they would show up as missing energy. The higher collision rates would make rare events more common. But the project faces challenges. The cost is estimated at over $20 billion. Construction would take decades. The tunneling alone is a massive civil engineering project passing through different rock layers and beneath bodies of water. Some physicists argue the money would be better spent on smaller, more targeted experiments. Others believe the discovery potential justifies the investment. The debate continues in scientific committees and funding agencies around the world. What is certain is that the current machine will not last forever. The high luminosity upgrade to the LHC will increase collision rates starting in 2029. That will extend the physics reach for another decade, but eventually diminishing returns will set in. The same energy can only reveal so much. To go further, you need more energy. The future circular collider would provide it, or perhaps a different design. A muon collider that achieves high energies in a smaller ring. The technology is less mature, but the physics case is compelling. One way or another, humanity will build a bigger machine. The questions demand it. The universe refuses to give up its secrets easily. And the biggest question of all remains unanswered. What will break first, our understanding or the equations that have guided us this far? Deep in the mathematics of theoretical physics, there exists a particle that no experiment has ever seen. It carries no electric charge. It has no color charge. It barely interacts with anything in the standard model. Yet it might be everywhere. Physicists call it the dark photon. The ordinary photon mediates electromagnetism. It carries the force between charged particles. Every time you see light, feel warmth, or watch a magnet attract iron, photons are responsible. The dark photon would do the same thing, but for a hidden sector. Imagine a parallel world of particles that do not interact with ours through the usual forces. No electromagnetic attraction, no strong nuclear binding, no weak decay. Only gravity connects us, and gravity is far too weak to detect individual particles. But there might be a bridge. The dark photon could mix with the ordinary photon through a quantum effect called kinetic mixing. The mixing would be tiny, suppressed by factors of 1,000 or 1,000,000 or more, but it would not be zero. If dark photons exist and mix with regular photons, they could explain dark matter. The dark sector might contain its own particles, its own forces, its own complexity, dark atoms, dark chemistry, dark structures held together by dark electromagnetism, all of it invisible to us except through the gravitational pull we observe in galaxies. CERN has searched for dark photons. The signature would be distinctive. A collision produces energy that seems to vanish. The missing energy could be carried away by a dark photon, escaping the detector without triggering any sensors. Alternatively, the dark photon could decay back into ordinary particles. If it lives long enough, it would travel some distance before decaying, creating a displaced vertex that appears away from the collision point. Neither signature has been found. The searches have set limits. Dark photons, if they exist, must have certain properties. Their mixing with ordinary photons must be smaller than specific values. Their masses must lie outside certain ranges, but vast parameter space remains unexplored. The FASER experiment installed in a side tunnel near Atlas specifically hunts for long-lived particles that escape the main detector. Dark photons are among its targets. The SHIP experiment planned for the future would push sensitivity even further. Other theories propose different connections between dark and visible matter. Axions originally invented to solve a problem with a strong force could also constitute dark matter. Sterile neutrinos, hypothetical partners to the known neutrinos, are another candidate. All these particles share a common feature. They interact so weakly that finding them requires either enormous data sets or exquisitely sensitive detectors. CERN provides the data sets. Specialized experiments provide the sensitivity. The search is methodical. Each null result eliminates possibilities. Each improvement in technique opens new windows. Eventually, either something will appear in the data or the parameter space will shrink until the theories become untenable. The dark photon might be real, or it might be a mathematical mirage, a solution to equations that nature chose not to implement. Either answer teaches us something. But while theorists chased invisible particles, experimentalists found something unexpected in the collisions themselves, patterns that should not have been there. When lead nuclei collide at the Large Hadron Collider, thousands of particles spray outward. The debris forms patterns. Ripples and waves propagate through the expanding fireball. Physicists call this collective flow, and it reveals that the quark-gluon plasma behaves like a liquid. This was expected. Heavy ion collisions produce enough matter to establish collective behavior. The plasma is dense, the particles interact, hydrodynamics applies. But then physicists looked at proton-proton collisions. A proton is tiny compared to a lead nucleus. When two protons collide, far fewer particles are produced. The system should be too small for collective effects. Individual particle interactions should dominate. There should be no flow. There was flow. The patterns appeared in the data like ghosts. Correlations between particles that pointed to collective behavior, ridges and valleys in the angular distributions that matched the signatures of hydrodynamics. At first, physicists doubted the results. Maybe the patterns came from something else. Jets of particles spraying from hard collisions could mimic flow. Quantum correlations could produce similar effects. The analysis needed to be bulletproof. It was. Multiple experiments confirmed the finding. CMS, Atlas, and Alice all saw the same patterns. The effect appeared not just in proton-proton collisions, but also in proton-lead collisions where the asymmetry should have washed out any collective behavior. Something was creating droplets of quark-gluon plasma. In the smallest collisions, the droplets would be microscopic, a few femtometers across, smaller than a proton itself. They would exist for only a trillionth of a second before expanding and cooling into ordinary hadrons. Yet in that brief moment, they would flow. This discovery challenged the understanding of the strong force. Quark-gluon plasma was supposed to require a minimum amount of matter. Below that threshold, the system should behave like a gas, not a liquid. The proton-proton results suggested the threshold was lower than anyone expected. Or perhaps something else was happening. Alternative explanations exist. Color glass condensate, a theoretical state of matter where gluons dominate, could produce similar patterns without true thermalization. Quantum interference effects could mimic collective flow. The debate continues. What is certain is that even the simplest collisions at the LHC contain surprises. The machine was built to find new particles. Instead, it is also revealing new states of matter, new behaviors, new connections between quantum mechanics and thermodynamics. Every collision is an experiment within an experiment. The primary search for Higgs bosons and exotic particles continues. But alongside it, a secondary investigation probes the fundamental nature of the strong force itself. The universe does not separate neatly into categories. Those connections sometimes point toward dangers that physicists take very seriously. Before the Large Hadron Collider turned on, some people worried it would end civilization. The concerns came in several flavors: microscopic black holes, strange matter that converts everything it touches, vacuum decay triggered by high-energy collisions. Each scenario sounded terrifying. Each one was taken seriously by physicists who performed detailed calculations to assess the risks. The conclusion was unanimous. The collider is safe. Here is why. Cosmic rays have been bombarding Earth for billions of years. These are particles from space, protons, and heavier nuclei accelerated by supernovae and other violent events. Some cosmic rays carry energies far higher than anything the LHC produces. When a cosmic ray hits the atmosphere, it collides with air molecules. The physics is identical to what happens inside the collider. If microscopic black holes could form, they would have formed countless times in the atmosphere. If strange matter could propagate, it would have converted the Earth long ago. The planet still exists. The evidence is clear, but let us examine the specific fears. Microscopic black holes require extra dimensions of space to form at LHC energies. Some theories predict such dimensions exist. If they do, and if black holes form, those black holes would evaporate almost instantly through Hawking radiation. They would pose no danger. Even if Hawking radiation somehow failed, the black holes would be moving at nearly the speed of light. They would pass through Earth and continue into space, never accumulating enough matter to grow. Strange matter, also called strangelets, is a hypothetical form of matter containing strange quarks. In addition to up and down quarks, the fear was that strangelets might be more stable than ordinary matter and could convert everything they touch. But experiments have searched for strangelets. None have been found. And again, cosmic rays provide the decisive argument. High-energy collisions happen constantly on the moon, on neutron stars, on every rocky body in the universe. If strangelets were dangerous, we would see the evidence. Vacuum decay is the most exotic concern. The fear was that a high-energy collision might nucleate a bubble of true vacuum, destroying the universe. This misunderstands the physics. Vacuum decay, if possible, would require concentrating energy at a single point in a way that colliders cannot achieve. The energy densities in cosmic ray collisions exceed anything at CERN. If the vacuum were unstable to such triggers, it would have decayed billions of years ago. The LHC is safe. The calculations are robust. The cosmic ray argument is decisive. But the fears reveal something important about how people respond to the unknown. New knowledge feels dangerous. Pushing boundaries triggers anxiety. This is natural. It is also why science requires careful reasoning rather than intuition. The collider will not destroy the world. What it might destroy is our confidence that we understand everything. Gravity is weak. This sounds wrong. Gravity holds planets in orbit. It collapses stars into black holes. It shapes the entire structure of the universe. How can it be weak? Compare it to the other forces. An ordinary refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. The electromagnetic force in that tiny magnet overpowers the gravity of a planet with a mass of 6 trillion kilograms. The strong nuclear force is even more powerful. It binds quarks together so tightly that you cannot isolate a single quark no matter how much energy you apply. Gravity is weaker than these forces by a factor of 10 to the 38th power. That is a 1 followed by 38 zeros. An almost incomprehensible ratio. Why? This is called the hierarchy problem. There is no known reason why the forces should differ by such extreme amounts. The Standard Model offers no explanation. It simply takes the measured values as inputs and moves on. But physicists find this deeply unsatisfying. The problem gets worse when you consider the Higgs boson. Quantum corrections should push the Higgs mass up to enormous values close to the Planck scale, where quantum gravity becomes important. The Planck mass is about 10 to the 19th billion electron volts. The Higgs mass is 125 billion electron volts. The difference is 16 orders of magnitude. For the Higgs to have its observed mass, the quantum corrections must cancel almost perfectly. Different contributions must add up to nearly zero, leaving only a tiny residue. This cancellation appears fine-tuned to an absurd degree. Physicists call this the naturalness problem. Supersymmetry was proposed as a solution. For every particle in the Standard Model, supersymmetry predicts a partner particle with different spin. The quantum corrections from particles and their partners would cancel automatically, explaining why the Higgs is light. But supersymmetric partners have not been found. The LHC has searched extensively. If supersymmetric particles exist with masses below a few trillion electron volts, they should have appeared. They have not. The natural region of parameter space has been excluded. This does not kill supersymmetry entirely. The partners could be heavier, just beyond current reach, but the heavier they are, the more fine-tuning returns. The solution becomes less elegant. Other explanations exist. Extra dimensions could dilute gravity, explaining its weakness. Composite Higgs models could make the mass less sensitive to high-energy physics. The multiverse could select for light Higgs masses anthropically. None of these alternatives have direct evidence. The hierarchy problem remains unsolved. It sits at the heart of particle physics. a glaring sign that something is missing from our understanding. Either new physics will appear and explain the hierarchy, or physicists will have to accept that the universe simply is this way without deeper reason. Neither option is comfortable. For decades, supersymmetry was the leading candidate for physics beyond the standard model. It solved multiple problems simultaneously. It explained the hierarchy, it provided dark matter candidates, it unified the forces at high energies. The mathematics was beautiful. The predictions were specific. The particles should appear at the Large Hadron Collider. They did not appear. Run 1 of the LHC from 2010 to 2013 found no supersymmetric partners. Run 2 from 2015 to 2018 pushed the limits higher. Run 3 ongoing now continues the search. Nothing. The simplest versions of supersymmetry are now excluded. The partners cannot hide below certain masses. If they exist, they must be heavier or more cleverly concealed than the original theories predicted. Some physicists have abandoned supersymmetry. They argue the theory made predictions that failed. Science requires updating beliefs when evidence contradicts expectations. Others remain hopeful. They point out that supersymmetry has many variations. The minimal model might be wrong, but extended versions could still work. The partners might decay in unusual ways that escape detection. The spectrum might be compressed, making signals hard to distinguish from background. The LHC keeps searching. Recent analyses focus on challenging signatures, long-lived particles that travel visible distances before decaying. Compressed spectra, where the mass differences are small and the decay products are soft, are particularly difficult. Exotic scenarios where the usual signatures are absent. Each search requires dedicated analysis. Each null result constrains the parameter space further. The net tightens. If supersymmetric partners exist at masses accessible to the LHC, they are running out of places to hide. But what if they are simply too heavy? The high luminosity upgrade will increase the data by a factor of 10. The future circular collider would reach 7 times higher energies. If supersymmetry lives just beyond current reach, future machines might find it, or supersymmetry might be wrong. This would be a major shift for theoretical physics. Many careers were built on supersymmetric model building. Many hopes were pinned on its discovery. Acknowledging failure is difficult, but science demands honesty. The universe does not care what physicists find elegant. It does what it does. The job of experiments is to reveal what that is, regardless of theoretical preferences. Supersymmetry remains possible. It is not yet dead, but it is no longer the confident prediction it once was. The absence of signals has forced humility on a field that was perhaps too certain of its expectations. Whatever lies beyond the standard model, it is more subtle than anticipated. Finding it will require patience, creativity, and more data than any machine has yet produced. Neutrinos were supposed to be massless. The original standard model assigned them zero mass. They would travel at exactly the speed of light. They would come in 3 types: electron neutrinos, muon neutrinos, and tau neutrinos, and each type would remain fixed forever. Then experiments showed neutrinos oscillate. A neutrino created as one type can transform into another type as it travels. Electron neutrinos from the Sun arrive at Earth as a mixture of all 3 types. Muon neutrinos from cosmic ray showers change flavor before reaching underground detectors. This oscillation is only possible if neutrinos have mass. The masses are tiny, at least 1,000,000 times smaller than the electron mass, perhaps much smaller still. The exact values are unknown, but the differences between the masses have been measured through oscillation experiments. Why are neutrinos so light? The standard model has no answer. It was not built to accommodate massive neutrinos. Extensions are required. New particles, new interactions, new symmetries. One popular idea is the seesaw mechanism. If a very heavy right-handed neutrino exists, far heavier than any particle we have observed, it could partner with the ordinary neutrino in a way that suppresses the mass. The heavier the partner, the lighter the ordinary neutrino becomes. Like a seesaw, pushing down on one side lifts the other. The heavy partner would be too massive to produce at any current collider, but its existence would explain why neutrino masses are so small compared to everything else. Other explanations exist. Radiative mass generation, where the mass arises through loop diagrams, extra dimensions where neutrinos propagate into hidden space. Each proposal makes different predictions. CERN contributes to neutrino physics in indirect ways. The LHC produces enormous numbers of neutrinos in its collisions. Most escape undetected, but specialized experiments have begun catching them. In 2023, the FASR collaboration announced the first detection of collider neutrinos, opening a new window for study. The neutrinos seen at FASR have the highest energies ever observed from a controlled source. Studying their interactions tests the standard model in unexplored regimes. But the biggest neutrino mysteries will be solved by dedicated experiments. Facilities in Japan, the United States, and elsewhere send beams of neutrinos through the Earth to distant detectors. They measure oscillations with increasing precision. They search for differences between neutrinos and antineutrinos that could explain the matter-antimatter asymmetry. The neutrino sector hides secrets the LHC alone cannot reveal. But every piece of the puzzle connects. If new particles exist that generate neutrino masses, they might also affect processes at the LHC. The seesaw partners might leave traces in rare decays. The symmetries that protect neutrino masses might show up in other measurements. Everything is linked, and the deepest links might connect to forces we have never detected. 4 forces govern the universe. Gravity pulls masses together. Electromagnetism binds atoms and powers light. The strong force holds nuclei intact. The weak force enables radioactive decay. 4 forces, no more, no less. This has been the consensus for half a century. But what if there is a 5th? Hints have appeared over the years. Anomalies in experiments, unexplained results, data that does not quite fit the predictions. In 2016, a Hungarian laboratory reported something strange. They were studying the decay of an excited beryllium nucleus. The nucleus emits a gamma ray, which sometimes converts into an electron-positron pair. The angle between the electron and positron was measured precisely. There was a bump at a specific angle. More pairs appeared than the standard model predicted. The excess corresponded to a new particle with a mass of about 17 million electron volts, far lighter than the Higgs, but heavier than the electron. The team proposed a 5th force, mediated by a particle they called X17. Other laboratories tried to replicate the result. Some saw hints, others did not. The situation remains confused. The original Hungarian result has not been definitively confirmed or refuted. Theoretical physicists proposed models. A new gauge boson similar to the photon but much heavier and more weakly coupled. A dark photon with specific mixing parameters. A protophobic boson that interacts differently with protons and neutrons. CERN could contribute. If X17 exists, it might be produced in LHC collisions. The production rate would be low, but the clean signature of electron-positron pairs at a specific mass would stand out. Dedicated searches have been proposed. Other anomalies point in different directions. The muon magnetic moment, though now largely resolved, suggested for years that unknown particles were influencing the measurement. The proton radius puzzle, where different measurement methods gave different sizes, implied missing physics. Most anomalies fade with better data. Statistical fluctuations look like signals until more events wash them out. Systematic errors masquerade as discoveries until their sources are identified. But occasionally, an anomaly is real. The discovery of the positron began with an anomaly in cosmic ray data. The discovery of the neutrino began with missing energy in beta decay. The discovery of dark matter began with anomalous rotation curves in galaxies. Every confirmed discovery was once an unexplained blip. The 5th force might be noise, or it might be the next breakthrough hiding in plain sight. Scientists keep looking. They measure everything they can. They follow every lead, because the force that changes physics could be lurking in data that already exists. The standard model is not a final theory. Everyone agrees on this. It leaves too many questions unanswered. It contains too many arbitrary parameters. It fails to incorporate gravity, but no one knows what replaces it. The LHC was supposed to provide guidance. At energies around 1 trillion electron volts, new physics should appear. Supersymmetric partners, extra dimensions, compositeness, something. Nothing has appeared. The Higgs boson fits the standard model perfectly. No deviations in its couplings, no anomalies in its production, no signs of additional Higgs particles or exotic decay modes. The searches for new particles have set limits, not made discoveries. Squarks and gluinos, if they exist, must be heavier than 2 trillion electron volts. Extra gauge bosons must be heavier than 5 trillion electron volts. Excited quarks must be heavier than 6 trillion electron volts. The desert stretches farther than anyone expected. This creates a crisis for theoretical physics. The naturalness arguments that motivated supersymmetry appear to be failing. The universe seems fine-tuned after all, with no dynamical explanation for why the Higgs is light. Some physicists have proposed abandoning naturalness entirely. Perhaps the universe simply has arbitrary constants. Perhaps the anthropic principle selects for values compatible with observers. Perhaps our aesthetic preferences have no bearing on reality. Others insist new physics must exist. The hierarchy problem is real. Dark matter requires an explanation. The matter-antimatter asymmetry demands new CP violation. The evidence is indirect but compelling. The question is where the new physics hides. Maybe it is too heavy for the LHC. Future colliders with higher energies might find it. Maybe it is too weakly coupled. Specialized experiments targeting rare processes might detect it. Maybe it takes unexpected forms. Particles that live too long or decay too quietly or appear in channels no one thought to check. The standard model will break eventually. The only questions are when, where, and how. Every measurement at CERN is a test. Every analysis probes the edges. Every result either confirms what we know or reveals what we missed. So far, confirmation has dominated, but physics has surprised us before, and the biggest surprises often come from the places we least expect. The Large Hadron Collider has recorded roughly 300 trillion collisions since it began operating. Each collision is preserved as a digital record, a snapshot of what particles were produced and where they went. Most of that data has been analyzed. Papers have been written, results have been announced. The Higgs boson discovery came from the first few trillion collisions. The exotic particles came from later runs. The precision measurements keep improving with each addition to the data set. But analysis never truly ends. New techniques emerge. Machine learning algorithms find patterns that traditional methods missed. Improved calibrations change the interpretation of old measurements. Theoretical advances suggest new signatures to search for. Data that seemed fully exploited turns out to contain more information. The same collisions that discovered the Higgs are still being studied. Better understanding of backgrounds reveals smaller signals. Combinations of multiple channels increase sensitivity. What looked like featureless noise might harbor undiscovered particles. This is why data preservation matters. CERN maintains archives of everything the LHC has recorded. Future physicists with future tools will reanalyze what we collected. They might find things we could not see. Open data initiatives have released portions of the archive to the public. Researchers outside the collaborations can now access real collision data. Citizen scientists, students, and independent physicists all have the chance to make discoveries. The potential is enormous. A particle that decays in an unusual way might have been missed by standard searches. A correlation between variables might indicate new physics that no one thought to check. A subtle excess in the tails of a distribution might become significant when combined with other evidence. Every collision is a frozen moment of creation. The energy that existed in the first trillionth of a second after the Big Bang, compressed into a point smaller than an atom, recorded for eternity in silicon and magnetic tape. We do not yet know everything those records contain. The discoveries of the future might already be sitting in the data of the past, waiting for someone to ask the right question. In 2029, the Large Hadron Collider will transform. The high luminosity upgrade will increase the collision rate by a factor of 5 to 7. Where the machine now delivers around 1 billion collisions per second at full intensity, it will soon deliver up to 7 billion. More collisions mean more chances to find rare events. The Higgs boson, produced once in every 10 billion collisions, will appear more frequently. The exotic particles that require trillions of events to observe will become accessible. The precision measurements that are currently limited by statistics will improve dramatically. The upgrade requires new technology. Magnets near the collision points must focus the beams more tightly. The beams themselves will be restructured into denser bunches. The detectors must handle 10 times more simultaneous collisions without becoming overwhelmed. Radiation damage is a major concern. The increased collision rate means increased radiation. Components that function for years at lower intensity will fail much faster. Entire sections of the detectors are being rebuilt with radiation-hardened materials. Timing becomes critical when dozens of collisions occur simultaneously. The detectors must distinguish which particles came from which collision. New timing layers capable of measuring particle arrival to within a few tens of trillionths of a second are being installed. The data rate will explode. Current systems record about 1,000 collision events per second selected from the billion that occur. The high luminosity LHC will require smarter triggers that can identify interesting events faster. Machine learning algorithms will run in real time, filtering the data before it is recorded. The physics program is ambitious. Measure the Higgs self-coupling with enough precision to test the shape of the potential. Observe the rare decay of the Higgs to muon pairs with definitive significance. Search for supersymmetric particles in compressed spectra that current analyses cannot probe. Every component of the machine and its detectors is being improved. The project involves thousands of engineers and scientists from around the world. The cost is billions of dollars. The timeline stretches over a decade, but the payoff could be enormous. If new physics exists at masses just beyond current reach, the high luminosity LHC will find it. If the standard model has cracks that only appear with more data, they will become visible. The machine that discovered the Higgs boson is about to become far more powerful. What it reveals next could redefine everything. There is another way to reach high energies. Protons are messy. They are made of quarks and gluons, each carrying a fraction of the total energy. When protons collide, only some of that energy goes into creating new particles. The rest sprays outward as debris. Electrons are clean but light. They radiate energy when bent in a circle, limiting how fast they can travel in a ring of reasonable size. Muons might be perfect. A muon is 200 times heavier than an electron. It radiates far less when bent, so it can reach higher energies in the same size ring. But unlike a proton, a muon is fundamental. All its energy is available for creating new particles. A muon collider could achieve 10 trillion electron collisions in a ring only 6 miles around. That is nearly as much as the LHC delivers in a ring 3 times larger. The challenge is that muons are unstable. A muon at rest decays in about 2 microseconds. Even at high speeds, where time dilation extends its lifetime, it survives only long enough to circle a small ring a few thousand times. That is enough. Engineers would need to produce muons, cool them into a tight beam, accelerate them to high energy, and collide them before they decay. The entire process must happen in a fraction of a second. The technology does not yet exist, but development is underway. Laboratories in the United States, Europe, and Japan are testing components. Cooling techniques that slow muons without losing them have been demonstrated. Acceleration schemes that work on the required timescale have been designed. A muon collider might operate by the 2040s. The physics it could do is extraordinary. Direct production of Higgs bosons in the collision, possible because muons couple more strongly than electrons. Searches for new particles at energies far beyond the LHC. Precision measurements of the Higgs self-coupling with better accuracy than any hadron machine. The muon collider is a dream that might become reality. It represents a different philosophy than the future circular collider. Smaller, cheaper, more technically challenging, but potentially more rewarding. Which path the field takes depends on many factors: funding, technology development, scientific priorities, political will. What is certain is that humanity will not stop building colliders. The questions are too important. The mysteries are too deep. Somewhere, somehow, a machine will probe energies higher than the LHC. And that machine will either confirm what we believe or shatter it completely. Why is there something rather than nothing? This is not a poetic musing. It is a scientific problem with no solution. The Big Bang created matter and energy. Space and time emerged. The universe expanded from a hot, dense state into the vast, cold cosmos we see today. But why did it happen? What caused the initial conditions? What determined the laws that govern everything? Physics can describe the evolution of the universe from a fraction of a second after the Big Bang onward. It can calculate how particles formed, how atoms assembled, how stars ignited, how galaxies clustered. Physics cannot explain why there was a Big Bang at all. The standard model takes the laws as given. Certain particles exist. They have certain masses. They interact through certain forces. The equations work, the predictions match, but the equations do not explain themselves. Why these particles? Why these masses? Why these forces? Some physicists appeal to the multiverse. Perhaps all possible laws are realized somewhere. We observe the laws we do because they allow observers to exist. Other universes with other laws have no one to ask questions. This is not satisfying to everyone. It feels like giving up. It replaces one mystery with an infinite number of mysteries. Others hope for a deeper theory, a principle that determines everything uniquely, a mathematical structure so beautiful and inevitable that the laws could not have been otherwise. No such theory has been found. String theory was a candidate for decades. It promised to unify all forces and explain all parameters, but it turned out to have an enormous number of possible solutions. The landscape of string vacua contains more possibilities than atoms in the observable universe. We are back to asking why this vacuum, why this solution, why this universe. CERN cannot answer these questions directly, but every measurement constrains the possibilities. Every discovery narrows the range of viable theories. Every confirmation of the standard model tells us what the deeper theory must reproduce. The physicists smashing particles together are not just finding new particles. They are mapping the boundaries of human knowledge. Somewhere beyond those boundaries lies the answer. Or perhaps the answer is that there is no answer. The universe simply is. Existence requires no justification. Either possibility is profound. Every morning, physicists at CERN check the data. They scroll through plots and histograms. They compare observations to predictions. They look for the one thing that does not fit. Most days, everything fits. The standard model holds, the measurements match the calculations, the searches find nothing. The world continues as expected. But one day, something will be different. A bump in a distribution where no pump should be. An excess of events in a channel that should be empty. A measurement that deviates from the prediction by more than statistical chance allows. That will be the crack. The first sign that our understanding is incomplete. The thread that, when pulled, unravels the entire fabric of known physics. It might come from the Higgs boson, a coupling that does not match, a decay mode that violates expectations, a partner particle hiding just beyond current reach. It might come from dark matter, a missing energy signature that cannot be explained, a particle escaping the detector that leaves just enough trace to be identified. It might come from something no one predicted, a new force, a new symmetry, a new dimension of space, something so unexpected that current theories have no name for it. The crack is coming. Physics guarantees it. The standard model cannot be final. It does not include gravity. It does not explain dark matter. It does not account for the matter-antimatter asymmetry. It contains too many arbitrary numbers with no deeper explanation. Something more fundamental exists. CERN is the tool that will find it. 17 miles of tunnel, thousands of scientists, trillions of collisions, all focused on one goal: to find the crack that unravels everything we know. The search has been running for decades. It will continue for decades more. And when the crack finally appears, when the data shows something impossible, when the equations fail and the theories crumble, that will be the greatest day in the history of physics. Because finding what breaks is the only way to learn what is truly real. The universe has been hiding its secrets for 14 billion years. We are getting closer. At 4 points around the 17-mile ring, the particle beams cross. These crossing points are surrounded by machines so large they dwarf everything humans have built for science. Atlas is one of them. The detector stands 7 stories tall and stretches half the length of a football field. It weighs 7,000 tons, more than the Eiffel Tower, more than 100 fully loaded passenger jets. Yet it measures particles smaller than atoms, with precision finer than a human hair. The name stands for a toroidal LHC apparatus. The toroidal part refers to the massive magnets that bend charged particles as they fly outward from collisions. By measuring how much each particle bends, physicists determine its momentum. The detector is built in layers like an onion. The innermost layer tracks particles closest to the collision point. Silicon sensors arranged in cylinders and disks record the paths of charged particles with micrometer precision. Billions of sensor channels feed data to computers that reconstruct the trajectories. Surrounding the tracker is the calorimeter. This layer stops particles and measures their energy. Electrons and photons deposit energy in the electromagnetic section. Hadrons penetrate deeper into the hadronic section. By the time particles reach the outer edge, almost nothing escapes except muons. Muons are heavy enough to punch through the calorimeter without stopping. The outermost layer of Atlas is dedicated entirely to catching them. Chambers filled with gas detect the ionization trails muons leave behind. The toroidal magnets bend their paths, allowing momentum measurement even at the detector's edge. CMS takes a different approach. The compact muon solenoid is smaller than Atlas, but heavier. 14,000 tons packed into a cylinder about 50 feet long. The word compact is relative. Where Atlas uses toroidal magnets, CMS uses a solenoid. A single superconducting coil generates a magnetic field 100,000 times stronger than Earth's. This field bends particles inside the detector, allowing precise tracking in a smaller volume. The two detectors were designed independently by competing collaborations. They use different technologies, different analysis methods, different teams of physicists. This redundancy is intentional. When both detectors see the same signal, it is almost certainly real. The Higgs boson discovery required both. Atlas found a bump at 125 billion electron volts. CMS found the same bump, two independent measurements, two independent confirmations. The probability of both being wrong was vanishingly small. Every major result from CERN follows this pattern. The detectors operate continuously when the beams are running. Collision after collision, hour after hour, year after year. The sensors degrade from radiation, components fail and are replaced. The machines age but keep working. When protons collide at the Large Hadron Collider, the detectors record everything. Particle tracks, energy deposits, timing information. Each collision generates roughly 1 megabyte of data. 600 million collisions happen every second. Recording all of them is impossible. The data rate would exceed the total storage capacity of the planet within hours. So the detectors make choices. Trigger systems analyze each collision in real time. Hardware circuits faster than any computer. Examine the raw data and decide within microseconds whether the event is interesting. Most events are discarded instantly. Only about 1/1000 per second survive the first filter. Software triggers examine the survivors more carefully. Algorithms reconstruct particle tracks and calculate energies. Events that might contain Higgs bosons, exotic particles, or unexpected signatures are kept. Everything else is thrown away. What remains is still enormous. Roughly 100 petabytes of data are recorded each year. That is 100 million gigabytes, enough to fill 20 million DVDs, enough to store every book ever written 1,000 times over. No single computer can analyze this. CERN built the worldwide LHC computing grid, a network of over 170 computing centers in more than 40 countries. The data flows from Geneva to laboratories around the world where thousands of processes work in parallel. The grid operates continuously. When physicists in Europe sleep, physicists in Asia continue the analysis. When Asia sleeps, the Americas take over. The computation never stops. Machine learning has transformed the analysis. Neural networks trained on simulated data learn to recognize patterns that indicate rare events. They find Higgs bosons hiding in backgrounds. They identify exotic particles that would escape traditional methods. They extract information from data that humans could never process. The algorithms improve constantly. Techniques developed last year become obsolete. New architectures, new training methods, new ways of combining information push the sensitivity higher. A discovery that would have taken a decade of analysis 20 years ago can now be made in months. But the machines do not think alone. Behind every algorithm is a physicist who designed it. Behind every result is a collaboration that checked it. The grid amplifies human intelligence. It does not replace it. Somewhere in those 100 petabytes, patterns await discovery. The question is whether we are asking the right questions to find them. The CERN Control Center operates around the clock, 3 shifts, 8 hours each. Physicists and engineers watching screens, monitoring systems, keeping the machine alive. At midnight, the room is quiet. A handful of operators sit at consoles arranged in a semicircle. Screens display beam positions, magnet currents, vacuum pressures, cryogenic temperatures, thousands of parameters, all within acceptable ranges. Green lights across the board. The beams circle the ring in opposite directions. 11,000 laps, billions of protons in each bunch traveling so close to the speed of light that time dilates measurably. Most nights are routine. The operators watch for anomalies: a magnet that warms slightly, a vacuum gauge that flickers, a beam that drifts from its ideal orbit. Small problems are corrected before they become large ones. But some nights are different. In 2015, a weasel chewed through a power cable and shut down the machine. In 2016, a tiny piece of baguette dropped by a bird caused a similar failure. The operators have learned to expect surprises. When something goes wrong, the response is immediate. The beam dump system can extract all the stored energy in less than a millisecond. Graphite blocks absorb the protons safely. The magnets ramp down. The machine goes silent. Then the diagnosis begins. Engineers descend into the tunnel to inspect equipment. Sensors are checked, connections are tested, the cause is found and fixed. The machine restarts. The process can take hours or weeks, depending on the problem. During physics runs, the pressure is constant. Every hour of downtime is an hour of lost data. Every lost collision is a lost chance at discovery. The operators balance caution against urgency. When the beams are stable and collisions are happening, the control room relaxes slightly. The screens show luminosity climbing, the detectors record events, data flows to the grid. This is what the machine was built for. 14 years of construction, billions of dollars, thousands of people, all for those moments when protons meet and the universe reveals another secret. The operators at midnight are guardians of that mission. They watch the screens, they wait for anomalies, and they know that any night could bring the signal that changes everything. Not every collision can be saved. The choice of what to keep determines what discoveries are possible. This is the trigger problem. 600 million collisions per second, each one potentially containing something new, but only 1,000 can be recorded. The rest are lost forever, their information discarded before any human ever sees it. How do you choose? The trigger system makes decisions in stages. The first level uses custom hardware circuits designed specifically for speed. They examine the detector signals and identify events with high energy particles, unusual patterns, or missing energy. These events pass to the second level. Software algorithms running on farms of computers analyze the survivors in more detail. Tracks are reconstructed. Masses are calculated. Events that look like known physics are rejected. Events that look unusual are kept. The criteria are carefully designed. Physicists simulate what new particles might look like. They calculate the signatures that would appear in the detector. Then they program the triggers to catch those signatures. But here's the danger. If you only trigger on what you expect, you only find what you expect. Truly unexpected physics might produce signatures no one anticipated. Those events would be discarded. The discovery would be lost. This keeps physicists awake at night. To guard against missing the unexpected, the triggers include general categories. Events with very high energy, regardless of what produced them. Events with unusual combinations of particles. Events that simply look strange. Some bandwidth is reserved for random sampling. A fraction of all events chosen without any selection criteria are saved for later study. If something unexpected is happening in the collisions, it might show up in these unbiased samples. The trigger menus are updated constantly. As new theoretical ideas emerge, new triggers are added. As old searches are completed, their triggers are retired to make room. The system evolves with the science. Artificial intelligence is changing the game. Neural networks can analyze events faster and more flexibly than traditional algorithms. They can learn to identify anomalies without being told exactly what to look for. The next generation of triggers will be smarter than anything that came before. But the fundamental problem remains. Most of what happens in the collider is thrown away. The discoveries we make depend on the choices we made about what to keep. Somewhere in the discarded data, there might be answers we will never know. Not all experiments at CERN search for the heaviest particles. Some search for the rarest decays. LHCb specializes in beauty. Beauty quarks, also called bottom quarks, are the second heaviest quark flavor. They live just long enough to travel a fraction of a millimeter before decaying. That tiny distance is measurable. It leaves a signature that LHCb was designed to catch. The detector looks different from ATLAS and CMS. Where those detectors surround the collision point symmetrically, LHCb extends in only one direction. It is a forward spectrometer built to catch particles that fly along the beamline. This is where beauty quarks tend to go. The physics is subtle. Beauty quarks decay through the weak force. The decay can happen in multiple ways, with different particles appearing in the final state. By measuring how often each decay mode occurs, physicists test the standard model with extreme precision. Tiny deviations could reveal new physics. If an unknown particle interferes with the decay, the branching ratios would shift. The CP violation would change. The angles and phases would differ from predictions. LHCb has found no clear deviations, but the measurements have reached unprecedented accuracy. The constraints on new physics are tighter than ever. Whatever lies beyond the standard model, it must be subtle enough to hide from these tests. Strange quarks tell a similar story. They are lighter than beauty quarks, but still unstable. Their decays probe the weak force in complementary ways. Experiments at CERN and elsewhere have studied strange particles for decades. The combined picture is consistent. The standard model describes flavor physics with remarkable success. The CKM matrix, which encodes how quarks mix and transform, matches the data within uncertainties. But puzzles remain. Why does the mixing matrix have the specific values it does? Why are some entries large and others small? The standard model provides no explanation. It simply takes the measured values as inputs. A deeper theory would predict them. LHCb continues to search. New decay modes are studied, new observables are measured. The precision frontier advances alongside the energy frontier. If the standard model has hidden cracks, the beauty quarks might reveal them, and if not, the measurements still constrain whatever comes next. In the first trillionth of a second after the Big Bang, the universe underwent a transformation. Before the transition, all particles were massless. The electromagnetic and weak forces were unified. The Higgs field had not yet settled into its valley. Everything moved at the speed of light. Then the universe cooled. The Higgs field rolled from the center of its potential into the ring of minima. Symmetry broke. The weak force separated from electromagnetism. Particles acquired mass. This was the electroweak phase transition. The details matter enormously. If the transition was smooth, like ice gradually melting into water, certain theories work. If the transition was violent, like water suddenly boiling, different theories apply. A violent transition could explain the matter-antimatter asymmetry. In a first-order phase transition, bubbles of the new phase form and expand. The walls of these bubbles are regions of extreme physics. Particles interact with the bubble walls in ways that might favor matter over antimatter. The standard model predicts a smooth transition with the measured Higgs mass. The mathematics say the transition was gentle. No bubbles, no walls, no mechanism for baryogenesis. This is a problem. The universe contains far more matter than the standard model can explain. If the electroweak transition was smooth, something else must have created the asymmetry. Extensions to the standard model could make the transition violent. Additional Higgs particles would change the potential. Supersymmetric partners would alter the calculations. New scalar fields could trigger stronger phase transitions. CERN searches for these extensions. If they exist, they would affect Higgs boson properties, deviations in couplings, exotic decay modes, associated production of new particles. So far, nothing has been found, but the measurements are not yet precise enough to rule out all possibilities. The high luminosity upgrade will improve sensitivity. The future circular collider would improve it further. The electroweak phase transition happened once 14 billion years ago. We cannot repeat it directly. But we can study the particles involved and infer what happened. The Higgs boson carries the memory of that moment. Measuring it precisely is like archaeology at the smallest scales, digging through layers of quantum effects to uncover what the universe looked like when it was younger than any word can describe. The strong nuclear force has a strange property. It should violate symmetry, but it does not. In quantum chromodynamics, the theory of the strong force, there's a term in the equations that would cause CP violation. This term is allowed by all the symmetries of the theory. There is no mathematical reason for it to be zero. Yet experiments show it is zero or at least undetectably small. The neutron has no measurable electric dipole moment. If the strong CP violation term were significant, the neutron would be asymmetric, with positive charge shifted slightly relative to negative charge. Experiments have searched for decades. The upper limit keeps dropping. The term must be smaller than 1 part in 10 billion. Why? This is the strong CP problem. A parameter that could be anything is instead almost exactly zero. Nature seems fine-tuned in a way that demands explanation. One solution involves a new particle. In the late 1970s, physicists proposed a mechanism that would dynamically set the problematic term to zero. The mechanism requires a new symmetry, and that symmetry predicts a new particle. They called it the axion. Axions would be extremely light and extremely weakly interacting. They would pass through ordinary matter without effect. They would be produced in the early universe and persist today. They might be dark matter. If axions have the right mass and abundance, they could account for the missing mass in galaxies. They would form a cold, diffuse background, invisible to all our detectors except through their gravitational effects. CERN has limited ability to search for axions directly. The particles are too light and too weakly coupled to producing collisions. Dedicated experiments using strong magnetic fields and sensitive detectors are better suited to the task, but CERN contributes indirectly. The physics of axions connects to the physics of the Higgs and the strong force. Measurements at the LHC constrain models that predict axion-like particles with different properties. The precision frontier supports the search. If axions are found, they would solve two problems at once: the strong CP problem and the dark matter mystery. A single particle explaining both. That kind of elegance is what physicists dream about. The universe might be messier than our dreams, but sometimes nature surprises us with simplicity. The Large Hadron Collider is not the only path forward. Around the world, physicists are designing machines that take different approaches. Some are larger, some are smaller. Some use particles that CERN has never collided. In China, plans exist for the Circular Electron-Positron Collider, a ring 62 miles around, similar to the proposed Future Circular Collider in Europe. It would produce Higgs bosons through electron-positron annihilation, measuring their properties with unmatched precision. The project has faced delays. Funding remains uncertain, but if built, it would advance the field significantly. In Japan, the International Linear Collider has been discussed for decades. Unlike circular machines, it would accelerate electrons and positrons in a straight line. No synchrotron radiation losses, higher energies possible in a given length. The design is ready. The site has been selected, but Japan has not committed to hosting the project. International negotiations continue. In the United States, concepts for a muon collider are advancing. The technical challenges are immense, but the physics potential is extraordinary. 10 trillion electron volts in a ring only miles across. If the technology works, it could leapfrog everything else. There are also smaller experiments that punch above their weight. Fixed target experiments smash beams into stationary blocks of material. The collision energy is lower, but the intensity can be enormous. Rare decays and exotic particles that require billions of events become accessible. Neutrino experiments send beams through the Earth. The particles oscillate over hundreds of miles, revealing properties that colliders cannot measure directly. Underground detectors wait for dark matter to strike. Tons of ultra-pure material sit in silent darkness, watching for the faint signal of a collision that happens maybe once per year. Space telescopes observe cosmic rays with energies far beyond any machine. Natural accelerators powered by supernovae and black holes produce particles we could never make. The LHC is one tool among many. Each approach reveals different aspects of nature. Each has strengths and limitations. The field advances on multiple fronts simultaneously. No single machine will answer all questions, but together they map the territory of the unknown. The nightmare scenario for particle physics is simple. The LHC completes its full program. The high luminosity upgrade runs for decades. Every analysis is performed. Every channel is searched. Nothing new is found. The standard model holds perfectly. No deviations, no anomalies, no cracks. This is not impossible. The Higgs boson might be exactly as predicted. The measurements might match calculations within ever-shrinking uncertainties. The searches might set limits that push new physics beyond any machine we can build. Uh, what then? Some physicists argue this outcome would still teach us something. The absence of new physics at the weak scale would rule out naturalness as a guiding principle. The fine-tuning of the Higgs mass would have to be accepted or explained some other way. The multiverse might become the default explanation. Our universe would be one of countless possibilities, selected anthropically for conditions compatible with observers. Others reject this conclusion. They argue that absence of evidence at one energy scale does not mean absence of physics at all scales. New particles might be heavier than any collider can reach. New forces might be weaker than any experiment can detect. The unknown would remain unknown, but not unknowable in principle. Funding agencies would face difficult decisions. Building larger colliders costs billions of dollars. If the last machine found nothing, would taxpayers support the next one? Would governments invest in projects that might also find nothing? The sociology of physics would shift. Young scientists might choose other fields. Bright minds that would have become particle physicists might become quantum computer engineers or biologists instead. The talent pipeline would narrow. History offers some comfort. After the discovery of the electron in 1897, physics seemed nearly complete. Lord Kelvin reportedly said only 2 small clouds remained on the horizon. Those clouds became relativity and quantum mechanics. After the completion of the Standard Model in the 1970s, some thought the end was near. Then came dark matter, dark energy, neutrino oscillations. Physics has surprised us before. The deepest discoveries often come when the field seems stuck. But waiting for surprise is not a strategy. The machines must be built. The data must be collected. The analyses must be performed, even if the answer is silence. Science requires asking the question. Imagine the morning it happens. A graduate student is checking plots, routine analysis, the same histograms they have examined 100 times before. Background estimates, signal regions, statistical tests. Something is different. A bump where no bump should be. An excess of events at a specific energy. Too many to be fluctuation. Too sharp to be background. They check their code. They rerun the analysis. The bump persists. They tell their supervisor. The supervisor tells the collaboration. Word spreads quietly through encrypted channels. Do not tell anyone outside. Not yet. Not until we are sure. More physicists examine the data. Independent analyses using different methods reach the same conclusion. The excess is real. The significance climbs. 3 sigma, the threshold where physicists start paying attention. 4 sigma, a strong hint, but not yet discovery. 5 sigma, the standard for claiming something new. The collaboration schedules a meeting. In a packed auditorium, senior physicists present the results. Slides show the histograms, the fits, the statistical tests. The room is silent except for the click of advancing slides. 5.3 sigma. The probability of a fluctuation is less than 1 in 3 million. Applause erupts. Some people cry. Years of work, decades of preparation, careers spent waiting for this moment. The discovery is announced to the world. Press conferences, headlines, television coverage. The particle is given a name. The theorists scramble to explain it. Everything changes. Textbooks must be rewritten. Curricula must be updated. The next generation of experiments must be planned. The career of every physicist in the room shifts toward understanding what was found. Some discoveries confirm what we expected. The Higgs boson matched predictions almost perfectly. Other discoveries shatter expectations. The accelerating expansion of the universe came from nowhere. Dark energy was not predicted by any mainstream theory. The next discovery could be either kind. It might fit neatly into an extension of the Standard Model. Supersymmetry finally confirmed. Extra dimensions revealed. A 4th generation of quarks completing a pattern, or it might be something no one imagined. A violation of Lorentz invariance, a breakdown of quantum mechanics at high energies, a signal from a sector of physics that has no name yet. We do not know what CERN will find, but we know the machines will keep running. The data will keep accumulating. The analyses will keep improving. One day, the plots will show something new. The crack will appear and physics will begin again. The search will never truly end because the universe is infinite in its complexity, and our understanding will always be incomplete. But that incompleteness is not a failure. It is an invitation. An invitation to keep asking questions, to keep building machines, to keep pushing into the dark. Because somewhere in that dark waiting for us is the next great discovery. And when we find it, we will remember this moment, this time when we stood at the edge of understanding and wondered what lay beyond. We will remember the machine beneath the Alps, the frozen ring of magnets and helium, the billions of collisions that revealed the hidden structure of reality. We will remember that we asked the question and we did not stop until we found the answer. The tunnel still stretches beneath the farmland. The cows still graze above it. The church bells still ring across the valleys. But now, when you walk through those fields, you know what lies beneath your feet. You know about the protons screaming through the vacuum, about the magnets colder than deep space, about the collisions that recreate the birth of the universe. You know about the cracks that physicists are searching for, the tiny fractures in the equations that could unravel everything. And you know that one day, maybe soon, maybe in a decade, maybe in a generation, someone will find one. And when they do, the world will change. Not because the world itself changes, but because our understanding of it will be transformed. And that transformation will ripple through everything, through science and technology, through philosophy and religion, through how we see ourselves and our place in the cosmos. This is what the machine beneath the Alps represents. Not just a scientific instrument, but a monument to human curiosity, a testament to our refusal to accept ignorance, a declaration that we will not stop asking why, even when the answers are uncomfortable, even when they threaten everything we believe. The physicists at CERN are not just searching for particles. They are searching for the truth about what we are made of and why we exist. And that search, that endless, relentless, beautiful search, is what makes us human. The protons will keep circling. The magnets will keep bending their paths. The detectors will keep recording their collisions. The data will keep flowing to the grid. The analyses will keep improving. And somewhere in that vast ocean of information, the answer is waiting. The crack is waiting. The discovery that changes everything is waiting. We just have to keep looking. We just have to keep asking the questions. We just have to keep pushing into the dark, knowing that somewhere beyond the edge of what we know, the light is waiting. And when we finally reach it, we will understand what the universe has been trying to tell us all along. We will understand the crack that unravels everything, and we will be ready.